Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet violence that shapes Enceladus, Saturn's ice moon, where radiation writes its story in molecular script across frozen plains. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Far beyond Mars, beyond the asteroid belt, beyond Jupiter's storms, Enceladus drifts through Saturn's magnetosphere like a small white pearl caught in an invisible web of charged particles. The moon measures only 500 kilometers across, small enough to nestle comfortably within the borders of Spain, yet it moves through one of the most radiation-rich environments in the outer solar system. Saturn's magnetic field, stretching millions of kilometers into space, traps electrons and protons from the solar wind, accelerating them to tremendous energies before hurling them toward anything that crosses their path. The magnetosphere itself presents a marvel of invisible architecture, generated deep within Saturn's metallic hydrogen core. Magnetic field lines spiral outward like the spokes of some cosmic wheel, creating zones of varying particle density and energy. Scientists measure the magnetic field strength at Enceladus's orbit at roughly 20 times Earth's surface magnetism, though this comparison fails to capture the true complexity of the system. Unlike Earth's relatively stable dipole field, Saturn's magnetosphere wobbles and fluctuates with the planet's rotation, creating a dynamic environment where radiation levels shift and pulse with predictable rhythms. The surface of Enceladus receives this bombardment with the patience of geological time. Each second, trillions of high-energy particles strike the frozen plains, the ancient craters, the fractured ridges that map the moon's surface like the lines on an aged hand. Most of these particles possess energies measured in kilo-electron volts, enough to shatter the delicate hydrogen-oxygen bonds that hold water molecules together, yet so small that their individual impacts pass unnoticed by any human observer. The moon's albedo, reflecting over 90% of incident sunlight, creates a surface so bright that it would blind any unprotected human eye. Yet this same pristine whiteness makes the radiation damage all the more subtle and profound. Scientists have calculated that a single square centimeter of Enceladus receives approximately 10 billion particle strikes each second. Only took 4.5 billion years of solar system formation to create such precise, relentless atomic artillery. The irony rests quietly in the mathematics. This moon, so distant from the sun that solar radiation barely whispers across its surface, bathes constantly in a different kind of cosmic violence, one manufactured by its own planetary host. The solar constant at Saturn's distance measures merely 1% of what Earth receives, yet the magnetospheric radiation environment exceeds terrestrial levels by factors of thousands. The geometry of bombardment follows patterns that would seem almost artistic if viewed from sufficient distance. Electrons, being lighter, spiral more tightly around magnetic field lines, creating focused beams that strike the surface at specific angles. Protons, nearly 2,000 times more massive, follow broader trajectories but carry correspondingly greater kinetic energy. The result resembles an invisible rain of varying droplet sizes, each carrying its own particular violence, falling upon a landscape that records every impact in molecular memory. The mystery deepens when researchers attempt to model exactly how this radiation penetrates the ice. Some particles strike the very surface layers, affecting only the topmost molecules in what scientists term the skin depth, a region extending perhaps only nanometers into the solid. Others, carrying higher energies, drill deeper, reaching perhaps several meters into the frozen crust before their momentum finally dissipates in cascades of secondary collisions. The Moon's weak gravity, barely 1% of Earth's, cannot hold an atmosphere thick enough to provide meaningful protection, leaving the ice exposed to every charged particle that Saturn's magnetosphere delivers. Recent measurements from the Cassini spacecraft revealed surprising variations in this bombardment pattern. The magnetic field lines do not strike Enceladus uniformly. Instead, they create preferential zones where particle flux concentrates. The leading hemisphere, which faces forward as the Moon orbits Saturn, receives roughly twice the radiation dose of the trailing hemisphere. This asymmetry creates a global pattern of chemical modification that maps directly onto Enceladus's orbital mechanics, turning the entire Moon into a slowly developing photograph of magnetospheric activity. Temperature plays a subtle but crucial role in this process. At Enceladus's distance from the Sun, surface temperatures hover around 60 Kelvin negative 213 degrees Celsius. At such extreme cold, ice crystals become nearly perfect, their molecular arrangements locked into rigid hexagonal patterns that can persist for millions of years. Yet even at these temperatures, radiation-induced chemical reactions proceed, albeit at rates measured in geological timescales. The cold actually preserves many radiation products that would decompose rapidly at higher temperatures, creating an archive of accumulated damage spanning eons. The Moon's famous tiger stripes the 4 parallel fractures near its south pole that spew water vapor into space, create local variations in the radiation environment. Where warm water emerges from the interior, it forms temporary clouds of vapor that partially shield the surrounding surface from particle bombardment. These regions experience slightly reduced radiation doses, creating chemical oases in an otherwise uniform field of molecular destruction. Only took millions of years of tidal heating and orbital mechanics to create these brief respites from cosmic bombardment. Between these countless impacts, Enceladus spins slowly on its axis, completing one rotation every 137 Earth days. The bombardment continues regardless, patient, steady, transforming ice one molecule at a time across eons that dwarf human comprehension. Each particle impact deposits energy, breaks bonds, rearranges atoms, and leaves behind microscopic alterations that accumulate like interest in some vast chemical bank account. The irony of protection emerges in the most unexpected places. Enceladus orbits within Saturn's E-ring, a tenuous collection of ice particles that the Moon itself produces through its geysers. These particles, while too sparse to provide meaningful shielding, occasionally absorb radiation that would otherwise reach the surface. The Moon thus creates its own partial protection, though at levels so minimal that the effect barely registers in scientific calculations. The universe, it seems, offers no free shelter from its own violence. The collision between a high-energy electron and a water molecule unfolds in femtoseconds, quadrillionths of a second, that stretch beyond human perception, yet contain entire universes of chemical possibility. When the electron strikes, it carries enough kinetic energy to overwhelm the electromagnetic forces that bind hydrogen to oxygen, severing bonds that have persisted since the ice first crystallized from primordial vapor. The water molecule, H2O in its simple chemical notation, becomes something else entirely, a hydroxyl radical, a free hydrogen atom, perhaps even individual oxygen and hydrogen ions that drift apart through the crystal lattice like survivors from some molecular shipwreck. This process, known as radiolysis, occurs billions of times each second across Enceladus's surface, yet each individual event remains invisible to direct observation. Scientists understand the mechanism through inference and measurement, detecting the cumulative products of countless molecular dissociations rather than witnessing the events themselves. The electron does not simply bounce off the water molecule like a billiard ball. Instead, it transfers its energy in quantum packets, exciting electrons within the water molecule to higher energy states until the molecular structure can no longer maintain its integrity. The chemistry becomes more complex as secondary reactions cascade through the ice crystal. A freed hydrogen atom, highly reactive and seeking chemical partnership, may encounter another hydrogen atom to form molecular hydrogen gas. Two hydroxyl radicals might combine to form hydrogen peroxide, a compound that remains stable in the extreme cold. Oxygen atoms, liberated from their watery bonds, can link together to form molecular oxygen O2, the same gas that sustains life on Earth, though here it emerges through purely abiotic processes in an environment where life could never survive. The energy budget of these reactions reveals profound ironies. Each water molecule requires approximately 10.8 electron volts of energy to break completely apart, roughly the same energy contained in a single photon of extreme ultraviolet light. Yet, the radiation environment around Enceladus delivers particles carrying hundreds or thousands of times more energy than necessary for basic molecular dissociation. Only took 4 billion years of planetary evolution to create such overwhelming overkill at the molecular level. The excess energy dissipates as heat, warming the ice by immeasurable amounts, or creates cascade reactions that affect neighboring molecules in expanding spheres of chemical influence. The crystal structure of ice itself influences how radiolysis proceeds. Water ice at Enceladus's surface, temperatures adopts what scientists call the hexagonal ice I phase, with each water molecule hydrogen bonded to 4 neighbors in a tetrahedral arrangement. This creates channels and spaces within the crystal lattice where freed radicals can migrate, sometimes traveling significant distances before encountering reaction partners. The ice acts simultaneously as the target of radiation damage and as the medium through which the products of that damage can spread and evolve. Temperature gradients within the ice create subtle variations in reaction rates and product stability. Near the surface, where temperatures remain constant at around 60 Kelvin, most radiolysis products freeze in place, preserved like insects in amber. Deeper in the crust, where tidal heating and radioactive decay from rocky components add fractional degrees of warmth, some products become mobile enough to migrate and react further. These temperature differences, measured in mere degrees across kilometers of ice, create distinct chemical environments stacked like geological layers. The mystery of product migration remains incompletely understood. Laboratory experiments on Earth cannot perfectly replicate the conditions found on Enceladus. The combination of extreme cold, high vacuum, and continuous low-level radiation bombardment over geological timescales exceeds the scope of terrestrial simulation. Scientists must extrapolate from short-term experiments to predict chemical evolution over millions of years, a process that introduces uncertainties and surprises. Recent theoretical models suggest that some radiolysis products might migrate through the ice over distances of meters or even kilometers, creating chemical heterogeneities that could persist for eons. The accumulation of these products follows patterns that would seem almost biological if observed in living systems. Hydrogen peroxide concentrations increase gradually over time until they reach equilibrium levels where production balances decomposition. Molecular oxygen builds up in pockets and bubbles within the ice, sometimes achieving pressures significant enough to affect the mechanical properties of the frozen crust. Hydrogen gas, being the lightest element, tends to escape from the ice and drift away into Saturn's magnetosphere, where it becomes part of the very particle population that created it in the first place. Spectroscopic observations from Earth-based telescopes and spacecraft instruments have detected many of these radiolysis products on Enceladus's surface. The signatures appear as subtle absorptions in reflected sunlight, dark lines in the spectrum where specific molecules absorb particular wavelengths. Hydrogen peroxide reveals itself through absorptions in the near-infrared, while molecular oxygen leaves fingerprints in the ultraviolet portion of the spectrum. These observations confirm theoretical predictions while raising new questions about the detailed mechanisms of radiation chemistry in extreme environments. The spatial distribution of radiolysis products across Enceladus's surface creates a chemical map that correlates directly with radiation exposure patterns. The leading hemisphere, which receives more intense particle bombardment, shows higher concentrations of oxidizing species like hydrogen peroxide and molecular oxygen. The trailing hemisphere retains more pristine water ice signatures, though even there, billions of years of continuous low-level bombardment have left their mark. The poles, where magnetic field lines converge and particle flux intensifies, display the strongest spectroscopic signatures of radiation damage. Only took millions of years for these chemical gradients to establish themselves across the Moon's surface. The irony of preservation emerges clearly. This radiation, violent enough to shatter molecular bonds, operates so slowly that its products accumulate and persist rather than being immediately destroyed. The cold serves as a molecular freezer, maintaining chemical inventory across geological timescales. Each impact adds to this inventory, while the extreme temperatures prevent rapid decay, creating an ever-growing library of radiation-induced chemistry. Between the quantum scale violence of individual particle impacts, vast regions of ice rest in perfect stillness, their molecular arrangements unchanged since the solar system's youth. Yet even in this apparent quiet, the slow chemistry of radiolysis continues, atom by atom, bond by bond, transforming Enceladus's surface into something subtly different from the pure water ice from which it began. Saturn's magnetosphere stretches across space like an invisible cathedral, its magnetic field lines forming vast arches that would dwarf continents if they were visible to human eyes, generated deep within the planet's interior, where metallic hydrogen flows in patterns driven by rapid rotation. This magnetic field extends outward for millions of kilometers before finally surrendering to the solar wind's relentless pressure. Within this magnetic realm, charged particles dance in complex spirals, trapped and accelerated by forces that operate according to the elegant mathematics of plasma physics. The architecture of this magnetosphere defies simple description. Unlike Earth's relatively stable magnetic dipole, Saturn's field wobbles with a period matching the planet's rotation, creating a dynamic environment where particle densities and energies shift in predictable cycles. The magnetic equator does not align perfectly with Saturn's rotational equator, introducing additional complexity as the entire system tilts and sways like some enormous cosmic gyroscope. These variations create regions of enhanced particle flux alternating with relative quiet zones, establishing patterns that Enceladus encounters as it follows its orbital path. Enceladus orbits Saturn at a distance of 238,000 kilometers, deep within the planet's magnetospheric domain. At this location, magnetic field strength measures approximately 300 nanotesla, roughly 6 times stronger than Earth's magnetic field at its surface. Though the comparison oversimplifies the true complexity of the environment, the field lines here do not run straight and uniform. Instead, They curve and twist in response to Saturn's rotation, creating a spiral pattern that resembles the grooves on some vast celestial record player spinning at 10 hours and 39 minutes per revolution. The particles trapped within this magnetosphere arrive from multiple sources, each contributing its own signature to the overall radiation environment. The solar wind provides a steady stream of electrons and protons, though these must first penetrate Saturn's magnetic barrier, a process that occurs primarily through magnetic reconnection events at the magnetopores. More exotic contributions come from Saturn's moons themselves. Titan's extended atmosphere leaks nitrogen and hydrocarbons into the magnetosphere, while volcanic Io-like processes on other satellites add heavier ions to the mix. Even Enceladus contributes to its own radiation environment through the water vapor it ejects from its south polar geysers. The energy distribution of these trapped particles follows what physicists call a power law spectrum, with vast numbers of low-energy particles and progressively fewer particles at higher energies. Electrons dominate the population numerically, outnumbering protons by factors of hundreds. Yet the protons carry proportionally more kinetic energy due to their greater mass. Alpha particles, helium nuclei stripped of their electrons, appear in smaller numbers but possess energies that can penetrate deeper into Enceladus's ice than their lighter counterparts. Only took 4.5 billion years of planetary evolution to create such precisely organized violence. The phenomenon known as magnetic mirroring plays a crucial role in determining how these particles interact with Enceladus's surface. As charged particles spiral along magnetic field lines, they encounter regions of increasing field strength that act like magnetic bottles, reflecting the particles back along their paths. This creates populations of particles that bounce back and forth between magnetic mirror points, following helical trajectories that can persist for hours or days before the particles finally precipitate onto a moon's surface or escape the magnetosphere entirely. Enceladus's weak gravitational field generating surface gravity of only 0.013 times, Earth's cannot significantly deflect these high-energy particles. Unlike larger moons such as Ganymede or Titan, which possess substantial atmospheres or magnetic fields of their own, Enceladus offers no meaningful protection against magnetospheric bombardment. The radiation environment treats the moon almost as if it were transparent, with particles striking the surface at energies and angles determined entirely by Saturn's magnetic field configuration. The temporal variations in this bombardment follow multiple overlapping cycles. Saturn's 11-hour rotation period creates the shortest-term variations, as regions of enhanced or depleted particle flux sweep past Enceladus like the beam of a lighthouse. The Moon's own 37-day orbital period introduces longer-term cycles as different hemispheres alternately face the more intense radiation zones. Even longer variations occur as Saturn's magnetosphere responds to changes in solar wind pressure and the 11-year solar cycle. Though these effects remain subtle compared to the dominant rotational and orbital patterns, recent observations have revealed that the magnetosphere exhibits what scientists term breathing behavior, periodic expansions and contractions of the entire magnetic cavity in response to solar wind pressure variations. During periods of high solar wind pressure, the magnetosphere compresses, concentrating particle populations and intensifying radiation levels throughout the system. When solar wind pressure decreases, the magnetosphere expands, diluting particle densities and providing brief respites from the most intense bombardment. These breathing cycles operate on timescales of hours to days, adding another layer of complexity to an already intricate system. The irony of magnetic protection becomes apparent when considering the larger context. Saturn's magnetosphere, which might seem to offer shelter from the harsh radiation environment of interplanetary space, actually creates a far more intense radiation field than anything Enceladus would experience if it orbited as a solitary body in the outer solar system. The magnetic field that traps and concentrates particles serves simultaneously as shield and weapon, protecting against some forms of radiation while generating others of greater intensity. Between the organized chaos of particle trajectories and magnetic field fluctuations, certain regions of space remain relatively quiet. These zones, often located between different particle populations or in the shadows of other moons, experience reduced radiation flux for brief periods. Yet even these comparative havens receive more high-energy particle bombardment than most locations in the inner solar system, illustrating the inherent violence of magnetospheric environments. The mystery of particle acceleration within Saturn's magnetosphere continues to challenge theoretical understanding. Some particles achieve energies that approach relativistic velocities, significant fractions of the speed of light, through mechanisms that remain incompletely explained. These ultra-high-energy particles, while rare, carry enough kinetic energy to penetrate kilometers into Enceladus's ice, creating deep chemical modifications that may persist throughout the Moon's geological lifetime. Only took millions of orbital revolutions for Enceladus to sample every variation and fluctuation in this magnetospheric environment. The Moon serves as both target and recorder of this invisible violence, its ice preserving the chemical signatures of radiation exposure across eons of steady bombardment. Within the crystalline lattice of water ice, each molecule occupies a precise position determined by the delicate balance of hydrogen bonds and electrostatic forces. At the temperatures that govern Enceladus's surface, 60 Kelvin, where molecular motion slows to near stillness, these ice crystals achieve a perfection that approaches the theoretical ideal. The hexagonal arrangement of water molecules creates channels and cavities with dimensions measured in angstroms, spaces so small that only individual atoms can navigate them, yet large enough to accommodate the wandering products of radiation damage. When a high-energy particle strikes this ordered world, it creates what solid-state physicists call point defects, individual locations where the perfect crystal structure becomes disrupted. The impact might displace a water molecule from its lattice position, creating a vacancy where a molecule should exist and an interstitial where a molecule exists where none should be. These defects represent stored energy within the crystal, like tiny springs compressed and waiting to release their tension when conditions permit. The most common defects created by radiation bombardment are known as Frenkel pairs, combinations of vacancies and interstitials that form when atoms are knocked from their regular positions but remain within the crystal. In water ice, these defects can involve entire water molecules or individual hydrogen atoms that have been separated from their parent molecules. The displaced species often settle into metastable positions within the crystal lattice, locations where they remain trapped by energy barriers that prevent immediate return to their original sites. Color centers represent another category of radiation-induced modification, though their effects on Enceladus remain subtle compared to the dramatic coloration seen in other irradiated materials. These defects involve electrons that become trapped at specific sites within the crystal, creating localized electronic states that can absorb particular wavelengths of light. On Enceladus, the formation of color centers contributes to the gradual yellowing and browning observed in heavily irradiated regions, though the effect requires millions of years to become spectroscopically detectable. The accumulation of these defects follows logarithmic rather than linear patterns, with the greatest changes occurring during the initial phases of bombardment and subsequent modifications proceeding at ever-decreasing rates. This saturation effect occurs because radiation damage creates its own limits. Defects can be destroyed as well as created by subsequent particle impacts, and the crystal eventually reaches an equilibrium state where creation and annihilation rates balance. Only took billions of years for Enceladus's surface to approach this equilibrium condition in its most heavily bombarded regions. Temperature plays a crucial role in determining which defects can persist and which undergo spontaneous healing. At the extreme cold of Enceladus's surface, most defects remain kinetically trapped in their metastable positions, unable to acquire sufficient thermal energy to migrate back to lower energy configurations. This kinetic trapping preserves radiation damage that would rapidly anneal at higher temperatures, creating an archive of bombardment history stretching back millions or billions of years. The spatial distribution of defects within individual ice crystals reveals patterns that reflect the physics of particle penetration. High-energy electrons create relatively uniform defect distributions throughout their range, while lower-energy particles produce concentrated damage near the crystal's surface. Protons, with their greater mass and charge, create dense tracts of damage along their trajectories, generating cylindrical zones of intense defect formation surrounded by regions of lesser modification. Advanced computational models suggest that some defects in Enceladus's ice exhibit remarkable longevity. Certain vacancy interstitial pairs, once formed, can persist for geological time periods without undergoing recombination. These stable defects effectively serve as permanent markers of radiation exposure, accumulating over time to create ice with physical and chemical properties distinctly different from the pristine material from which it formed. The modified ice becomes slightly less dense, exhibits altered optical properties, and shows enhanced reactivity towards certain chemical species. The phenomenon of defect clustering adds additional complexity to this picture. Individual point defects, while stable in isolation, can migrate slowly through the crystal lattice at rates determined by thermal activation and quantum tunneling effects. When two defects encounter each other, they may combine to form larger, more complex defect clusters that exhibit different properties from their isolated components. These clusters can serve as nucleation sites for further structural modifications or as traps that immobilize other mobile species within the ice. Recent theoretical work has identified the possibility of defect-mediated phase transitions within heavily irradiated ice. Under certain conditions, the accumulation of sufficient defect density might trigger local transformations from the normal hexagonal ice structure to amorphous or high-pressure ice phases. These transitions would occur at the microscopic scale, creating a heterogeneous material composed of multiple ice phases intermixed at the nanometer level, a structure unlike anything found naturally on Earth. The self-healing properties of ice introduce subtle ironies into the defect accumulation process. While most defects remain trapped by the extreme cold, certain particularly mobile species can undergo partial recovery even at Enceladus's surface temperatures. This recovery occurs through quantum tunneling effects that allow hydrogen atoms to traverse energy barriers that would be insurmountable through classical thermal activation alone. The result is a dynamic equilibrium where some defects heal while others accumulate, creating ice with properties that evolve continuously over geological time. The mechanical consequences of defect accumulation remain largely theoretical due to the difficulty of reproducing Enceladus conditions in terrestrial laboratories. Computer simulations suggest that heavily irradiated ice might exhibit altered fracture properties, different thermal conductivity, and modified response to tidal stresses. These changes could influence how Enceladus's crust responds to the tidal forces that drive its geological activity, creating feedback effects between radiation damage and tectonic processes. Only took millions of particle impacts to transform individual ice crystals from perfect hexagonal arrangements into complex assemblages of defects, clusters, and modified structures. The mystery of defect evolution continues over timescales that exceed direct observation, leaving scientists to infer the long-term consequences from theoretical models and limited experimental data. Between the quantum-scale precision of individual defect formation and the global consequences of accumulated damage, ice crystals on Enceladus preserve a molecular memory of every high-energy particle that has ever struck their surface. The irony of perfection emerges clearly. The most perfectly ordered crystal structures become the most sensitive recorders of disorder, preserving evidence of radiation bombardment in their altered arrangements for geological ages. Each defect represents a moment when cosmic violence overcame crystalline order, creating permanent testimony to the invisible forces that shape worlds in the outer solar system. Across the vast plains and ancient craters of Enceladus, a subtle transformation unfolds at wavelengths just beyond human perception. The pristine white surface, so reflective that it returns over 90% of incident sunlight back to space, slowly acquires hues that would escape casual notice yet speak volumes to sensitive spectrometers. In regions where radiation bombardment reaches its greatest intensity, the ice develops pale yellow tints reminiscent of aged parchment, while areas exposed to the most energetic particles evolve toward deeper amber and brown colorations that would seem almost organic if observed on any other world. These chromatic changes occur through processes that operate at the intersection of physics and chemistry, where high-energy particles create molecular fragments that absorb light selectively across the visible spectrum. The initial white appearance of water, ice results from its molecular structure. The hydrogen-oxygen bonds in H2O interact with visible light wavelengths in ways that cause uniform scattering rather than selective absorption. Pure water ice appears white for the same reason that fresh snow appears white. It reflects all visible wavelengths equally, creating the perception of colorless brightness. Radiation-induced coloration begins when particle bombardment breaks these pristine molecular arrangements and creates new chemical species with different optical properties. Hydrogen peroxide, one of the most abundant radiolysis products, absorbs strongly in the ultraviolet and weakly in the blue portion of the visible spectrum, contributing to subtle yellow tints in heavily irradiated regions. Molecular oxygen, trapped within the crystal lattice, introduces additional absorption features that enhance the yellowing effect. More complex organic molecules, formed through reactions between radiation products and trace carbon-bearing impurities, can produce deeper colorations ranging from amber to reddish-brown. The spatial distribution of these colors creates a map of radiation exposure that correlates precisely with magnetospheric bombardment patterns. Enceladus's leading hemisphere, which faces forward into Saturn's radiation belts during its orbital motion, displays the most pronounced coloration changes. Here, billions of years of enhanced particle bombardment have transformed the surface ice into material that spectroscopically resembles tea-stained paper more than pure frozen water. The trailing hemisphere retains more pristine coloration, though even there, subtle yellowing reveals the effects of continuous low-level radiation exposure. Spectroscopic observations reveal that these color changes occur not uniformly across the electromagnetic spectrum, but rather in discrete absorption bands that correspond to specific molecular transitions. Near-infrared wavelengths show particularly strong modification, with new absorption features appearing at 1.5 2.0 and 2.7 micrometers signatures that astronomers can detect from Earth-based telescopes despite the vast distances involved. Only took decades of careful spectroscopic monitoring to establish these correlations between radiation exposure and surface coloration. The temporal evolution of coloration follows complex patterns that depend on both the intensity and duration of radiation exposure. Initial bombardment creates dramatic changes in surface reflectance, with even modest radiation doses sufficient to produce detectable yellowing within thousands of years. Continued exposure drives the coloration toward deeper hues, though the rate of change decreases as the surface approaches equilibrium between color-producing and color-destroying processes. Some radiation-induced chromophores prove unstable under continued bombardment, decomposing into colorless products that restore some of the original ice brightness. Temperature variations across Enceladus's surface introduce additional complexity into the coloration process. The warmer regions near the south polar geysers, where temperatures may reach 90 Kelvin or higher, experience enhanced rates of chemical reaction that can both accelerate color formation and promote the destruction of previously formed chromophores. These thermal effects create local variations in surface coloration that superimpose additional patterns onto the global radiation exposure map. The mystery of color stability under extreme conditions continues to challenge theoretical understanding. Laboratory experiments conducted at terrestrial temperatures cannot accurately reproduce the conditions found on Enceladus, where chromophores must remain stable for millions of years at temperatures approaching absolute zero. Computer models suggest that some radiation-induced color centers might persist indefinitely under these conditions, while others could undergo slow degradation through quantum tunneling effects that operate on geological timescales. Recent spacecraft observations have revealed that the coloration patterns on Enceladus exhibit fine-scale structure that correlates with surface topography and geological features. Crater rims and fracture walls, which present different angles to the incident radiation flux, show distinctive coloration patterns that reflect variations in bombardment geometry. The famous tiger stripes near the South Pole display complex coloration variations that result from the interplay between radiation exposure, thermal activity, and the continuous deposition of fresh ice from geyser activity. The photochemical stability of these colors introduces ironic complications into the surface evolution process. While radiation creates the chromophores responsible for coloration, it also provides the energy necessary for their photochemical destruction. Ultraviolet radiation from Saturn's magnetosphere, the same radiation environment that produces the colored species, can break down complex organic molecules and restore some degree of original ice coloration. This creates a dynamic equilibrium where color formation and destruction proceed simultaneously at rates that vary with local radiation intensity. Comparative studies with other icy satellites reveal that Enceladus exhibits relatively subtle coloration compared to more heavily irradiated moons like Europa or Ganymede. This difference results partly from Enceladus's active geology, which continuously resurfaces portions of the Moon with fresh ice from the interior, effectively erasing the accumulated record of radiation damage. Only took millions of years of geological activity to establish this balance between surface renewal and radiation-induced modification. The wavelength dependence of coloration extends far beyond the visible spectrum into infrared regions where molecular vibrations create additional absorption features. These infrared signatures provide detailed information about the specific chemical species responsible for coloration, allowing scientists to distinguish between different radiolysis products and estimate their relative abundances. Hydrogen peroxide shows characteristic absorption at 3.5 micrometers, while organic sulfur compounds exhibit features near 4.0 micrometers. Between the quantum mechanics of electronic transitions and the geological processes that expose fresh ice to bombardment, Enceladus maintains surface colors that record the history of radiation exposure across multiple timescales. Each subtle hue represents millions of molecular modifications, accumulated over eons of patient bombardment by particles too small to observe individually, yet powerful enough to transform entire landscapes through their collective action. The palette of Enceladus thus becomes a form of cosmic art, painted by invisible brushstrokes of high-energy particles across a canvas of frozen water. Only the most sensitive instruments can detect these subtle colorations, yet they represent one of the most direct ways that radiation damage manifests itself to remote observers, creating beauty from violence across the vast emptiness of the outer solar system. In the silent laboratories of Enceladus's irradiated ice, oxygen emerges from water through processes that require neither the photosynthetic machinery of green plants nor the burning flames that humans associate with oxidation. Here, in temperatures so cold that the air itself would freeze solid, radiolysis performs the ancient alchemy of splitting water molecules, liberating oxygen atoms that have been bound to hydrogen since the ice first crystallized from primordial vapor. Each broken bond releases molecular oxygen into an environment where it can persist for geological ages, creating oxidizing conditions in a world that has never known fire, breath, or life. The quantum mechanics of water molecule dissociation under radiation bombardment follows pathways that seem almost purposeful in their efficiency. When a high-energy electron collides with a water molecule, it can transfer sufficient energy to promote one of the molecule's electrons to an excited state that renders the entire structure unstable. The excited water molecule may directly dissociate into hydrogen and hydroxyl radicals, or it may transfer its excess energy to neighboring molecules in a cascade of reactions that propagates through the crystal lattice like ripples across a frozen pond. The freed oxygen atoms face multiple possible fates within the ice crystal matrix. Two oxygen atoms encountering each other can combine to form molecular oxygen O2, the same diatomic molecule that constitutes 21% of Earth's atmosphere. This reaction occurs without the need for elevated temperatures or catalytic surfaces. The extreme cold actually favors the formation of molecular oxygen by preventing its rapid decomposition through thermal motion. The newly formed O2 molecules become trapped within the crystal lattice, occupying interstitial spaces or creating small bubbles that can grow through continued radiolysis. Alternatively, oxygen atoms may react with intact water molecules to form hydrogen peroxide, H2O2, a powerful oxidizing agent that remains remarkably stable under Enceladus's surface conditions. This reaction pathway becomes increasingly important as radiation damage accumulates, because hydrogen peroxide molecules can themselves undergo further radiolysis to produce additional oxygen atoms, creating autocatalytic cycles that amplify the oxidizing capacity of the irradiated ice. Only took millions of years for these chemical networks to establish themselves within the most heavily bombarded regions. The spatial distribution of oxygen production within Enceladus's ice follows patterns determined by the penetration depths of different radiation types. High-energy electrons create relatively uniform oxygen concentrations throughout their range, typically extending several centimeters into the ice surface. Protons, being more massive and carrying greater kinetic energy, can penetrate meters into the crust while creating dense tracts of radiolysis products along their trajectories. The result is a three-dimensional distribution of oxygen that varies with depth and location according to the local radiation environment. Spectroscopic observations from spacecraft and Earth-based telescopes have detected molecular oxygen signatures across much of Enceladus's surface, though the concentrations remain far below those found in planetary atmospheres. The oxygen appears primarily as absorption features in the near-infrared spectrum, where O2 molecules create characteristic bands at specific wavelengths. These observations confirm theoretical predictions about radiolytic oxygen production while revealing unexpected variations in concentration that correlate with surface geology and radiation exposure patterns. The escape of oxygen from Enceladus creates one of the solar system's most tenuous atmospheric phenomena. Some oxygen molecules acquire sufficient kinetic energy through additional radiation impacts to overcome the Moon's weak gravitational field and escape to space. This creates an extremely thin oxygen atmosphere, technically an exosphere with a surface pressure approximately 100 trillion times smaller than Earth's atmosphere. The escaping oxygen joins Saturn's magnetosphere, where it becomes ionized and contributes to the population of charged particles that created it in the first place. Temperature gradients within the ice introduce subtle but important effects on oxygen behavior. Near the surface, where temperatures remain constant at 60 Kelvin, most molecular oxygen remains trapped within the crystal lattice in a quasi-solid state. Deeper in the crust, where tidal heating and radioactive decay from rock components add fractional degrees of warmth, some oxygen molecules become mobile enough to migrate through the ice matrix. This migration can concentrate oxygen in particular regions, or allow it to escape through pathways that connect to the surface. The chemical reactivity of radiation-produced oxygen creates additional complexity in heavily irradiated ice. Molecular oxygen can react with organic compounds, trace amounts of carbon-bearing molecules that arrive via meteorite bombardment or emerge from Enceladus's interior to form more complex oxidized species. These reactions proceed slowly at the extreme surface temperatures, but can accelerate significantly in the warmer subsurface regions where most of the Moon's geological activity occurs. Recent theoretical models suggest that oxygen production rates on Enceladus may vary significantly over geological timescales in response to changes in Saturn's magnetosphere and the Moon's orbital characteristics. During periods when the magnetosphere contracts due to high solar wind pressure, Enceladus experiences enhanced radiation bombardment that accelerates oxygen production. Conversely, magnetospheric expansion during solar minimum conditions provides relative respites that allow previously formed oxygen to redistribute or escape without replacement. The preservation of oxygen within ice crystals represents a remarkable example of chemical storage under extreme conditions. Unlike terrestrial environments where oxygen readily reacts with available materials and disappears from the local environment, the pristine ice of Enceladus provides few reaction partners for the newly formed molecular oxygen. Combined with the kinetic limitations imposed by extreme cold, this chemical isolation allows oxygen concentrations to build up over millions of years to levels that would be unstable under more temperate conditions. The irony of oxidation without combustion becomes apparent when considering the broader implications of oxygen production on Enceladus. This moon, located in one of the most reducing environments in the solar system, far from the sun, and surrounded by hydrogen-rich compounds, nonetheless maintains surface conditions that are strongly oxidizing due entirely to radiation-induced chemistry. The oxygen exists in a world that could never support the fires that humans associate with oxidation, yet it creates chemical conditions more oxidizing than many terrestrial environments. Between the quantum-scale violence of molecular dissociation and the global accumulation of oxidizing species, Enceladus transforms water into oxygen through processes that operate continuously across geological time. Each liberated oxygen atom represents a small victory of cosmic radiation over molecular stability, contributing to chemical conditions that persist long after the particles responsible for their creation have dissipated their energy and become part of the crystalline matrix they helped to modify. Only took billions of particle impacts to establish the current oxygen inventory within Enceladus's ice. Yet this inventory continues to grow as radiation bombardment proceeds without pause. The mystery of oxygen distribution and behavior in such extreme environments continues to challenge scientific understanding, leaving researchers to infer long-term consequences from limited observations and theoretical models that approach but cannot fully capture the complexity of this alien chemistry. Above the frozen plains of Enceladus, individual atoms depart the solid surface one by one, in a process so gentle that it resembles evaporation more than the violent explosions that might be expected from high-energy particle bombardment. This phenomenon, known as sputtering, occurs when incoming radiation transfers sufficient momentum to surface atoms to overcome the weak binding forces that hold them within the ice crystal lattice. The ejected atoms carry with them kinetic energies that span a vast range, from barely escaping the surface to achieving velocities that exceed Enceladus's escape velocity and contribute directly to Saturn's tenuous E-ring. The physics of sputtering operates through collision cascades that begin when a high-energy particle penetrates the ice surface and transfers its kinetic energy to the surrounding crystal lattice through a series of atomic collisions. Each collision imparts momentum to lattice atoms, which then collide with their neighbors in expanding spheres of influence that can affect thousands of water molecules before the energy finally dissipates as heat. Most of these collision events result in atomic displacements that remain confined within the solid. But occasionally, the cascade reaches the surface with sufficient energy to eject atoms into the vacuum above. The sputtering yield. The number of atoms ejected per incident particle depends critically on the energy, mass, and angle of the bombarding radiation. Low-energy electrons typically produce yields of less than 1 atom per impact, while high-energy protons can eject dozens of water molecules through single collision events. The angular dependence follows patterns that reflect the geometry of collision cascades, with maximum sputtering occurring when particles strike the surface at angles between 45 and 60 degrees from the vertical. Normal incidence impacts, striking perpendicular to the surface, often produce lower yields because their energy dissipates deeper within the ice rather than near the sputterable surface layer. The energy distribution of sputtered atoms follows what physicists call a Thomson distribution, with most ejected particles carrying relatively low kinetic energies, while a small fraction achieves much higher velocities. This energy spectrum determines the fate of each sputtered atom. Low-energy ejector may fall back to the surface after brief ballistic trajectories, while high-energy atoms escape Enceladus's gravitational field entirely and enter independent orbits around Saturn. The intermediate energy population follows elliptical trajectories that may carry atoms hundreds of kilometers above the surface before gravity returns them to impact sites far from their points of origin. Enceladus's weak surface gravity, only 1.13% of Earth's gravitational acceleration, plays a crucial role in determining sputtering efficiency. The escape velocity from Enceladus measures merely 240 meters per second, a speed easily achieved by atoms energized through radiation-induced collision cascades. This low escape velocity means that a significant fraction of sputtered material permanently escapes the Moon's gravitational influence, creating a continuous mass loss that has persisted throughout the solar system's history. Only took billions of years for this gentle atomic erosion to remove entire meters of surface material from heavily bombarded regions. The composition of sputtered material reflects both the chemistry of the target surface and the preferential ejection of certain atomic species. Hydrogen atoms, being the lightest constituents of water ice, achieve the highest velocities during sputtering events and escape most readily from Enceladus's gravitational field. Oxygen atoms, nearly 16 times more massive than hydrogen, require proportionally more energy to achieve escape velocity and tend to remain gravitationally bound to the Moon. This selective escape creates chemical fractionation effects that gradually enrich the surface ice in heavier elements while depleting light isotopes and atomic species. The temporal evolution of sputtering rates depends on the accumulation of radiation damage within the ice surface. Fresh, crystalline ice exhibits different sputtering characteristics than heavily irradiated material with accumulated defects and chemical modifications. As radiation damage accumulates, the binding energy of surface atoms decreases, making them more susceptible to ejection through subsequent particle impacts. This creates positive feedback effects, where increased sputtering exposure leads to enhanced sputtering efficiency, accelerating the erosion rate in regions that already experience intense bombardment. Recent computer simulations suggest that sputtering from Enceladus operates in distinct regimes depending on the local radiation environment and surface composition. In regions dominated by electron bombardment, sputtering proceeds through relatively gentle mechanisms that preferentially eject individual atoms and small molecular fragments. Areas subjected to intense proton bombardment experience more violent sputtering events that can eject intact water molecules and larger clusters through single collision cascades. The contribution of sputtered material to Saturn's E-ring represents one of the most significant mass transport processes in the outer solar system. Enceladus loses approximately 150 kilograms of material per second through sputtering a rate that seems negligible compared to the Moon's total mass, but becomes geologically significant when sustained over millions of years. This sputtered material joins the much larger contribution from the south polar geysers to maintain the E-ring's distinctive composition and spatial distribution. Temperature effects introduce additional complexity into the sputtering process. While Enceladus's surface temperatures remain too low for significant thermal effects on sputtering yields, the energy deposited by radiation bombardment creates transient local heating that can influence ejection mechanisms. Computer models suggest that some high-energy impacts may create microscopic hotspots where temperatures briefly exceed the sublimation point of water ice, leading to explosive material ejection that supplements the more common collision cascade sputtering. The angular distribution of sputtered atoms follows patterns that reflect the crystalline structure of the target ice and the geometry of the collision cascades that produce them. Most sputtered material emerges within narrow angular cones centered around the surface, normal, though high-energy collision events can eject atoms in nearly any direction. This angular dependence influences how sputtered material redistributes across Enceladus's surface and determines which fraction escapes to contribute to the E-ring versus remaining gravitationally bound to the Moon. The mystery of sputtering efficiency under extreme conditions continues to challenge theoretical understanding. Laboratory experiments cannot fully reproduce the combination of ultra-high vacuum, extreme cold, and continuous low-level bombardment that characterizes Enceladus's surface environment. Scientists must rely on theoretical models and limited experimental data to predict sputtering behavior over geological timescales, introducing uncertainties in estimates of cumulative erosion and material loss. Only took millions of orbital revolutions around Saturn for sputtering to establish its current patterns across Enceladus's surface. The irony of gentle violence becomes apparent this process. So subtle that individual sputtering events remain invisible to direct observation, cumulatively reshapes entire landscapes through patient atomic erosion that operates continuously across geological time. Between the quantum-scale precision of individual collision events and the global consequences of accumulated material loss, sputtering transforms Enceladus atom by atom, contributing to the tenuous beauty of Saturn's ring system while slowly eroding the very world from which the ejected atoms originated. The lightest element in the universe, hydrogen, emerges from Enceladus's radiolyzed ice with velocities that carry it inexorably beyond the reach of the Moon's feeble gravitational embrace. Each hydrogen atom, liberated from its molecular partnership with oxygen through the violence of radiation bombardment, possesses a mass so minimal that even modest kinetic energies can accelerate it to speeds exceeding Enceladus's escape velocity of 240 meters per second. These freed atoms rise from the ice surface like invisible smoke, carrying with them the chemical memory of their violent separation while contributing to one of the solar system's most tenuous yet persistent atmospheric phenomena. The escape process begins at the moment of radiolytic dissociation, when water molecules fragment under particle bombardment to release hydrogen atoms with initial velocities determined by the quantum mechanics of molecular breakup. The typical hydrogen atom emerges from radiolysis carrying kinetic energy equivalent to several thousand Kelvin of thermal motion, far exceeding the 60 Kelvin surface temperature that governs the thermal behavior of intact water molecules. This initial velocity boost provides many hydrogen atoms with sufficient speed to escape immediately, though others may undergo additional acceleration through subsequent radiation impacts or thermal processes within the ice matrix. The ballistic trajectories of escaping hydrogen atoms follow parabolic paths determined by Enceladus's gravitational field and the atom's initial velocity vectors. Those launched vertically upward from the surface experience maximum gravitational deceleration but require the highest initial velocities to achieve escape. Atoms ejected at oblique angles follow longer trajectory paths that allow lower initial velocities to result in successful escape, creating a complex three-dimensional pattern of hydrogen efflux that varies with surface topography and local radiation conditions. The continuous loss of hydrogen through this process creates measurable chemical fractionation effects within Enceladus's ice, as the lighter isotope of hydrogen protium escapes preferentially due to its lower mass. The remaining ice becomes gradually enriched in deuterium, hydrogen's heavier isotope that contains an additional neutron in its nucleus. This isotopic fractionation occurs so slowly that direct measurement remains challenging. Yet theoretical models suggest that billions of years of preferential hydrogen escape have created detectable deuterium enrichment in the most heavily irradiated surface regions. The fate of escaped hydrogen atoms depends on their initial velocities and the complex dynamics of Saturn's magnetospheric environment. Atoms with velocities just exceeding escape velocity enter highly elliptical orbits around Saturn, where they may persist for months or years before eventually colliding with other satellites, falling into the planet's atmosphere, or achieving sufficient energy to escape the Saturnian system entirely. Higher velocity atoms follow hyperbolic trajectories that carry them directly out of Saturn's gravitational influence, contributing to the interplanetary medium throughout the outer solar system. Recent spacecraft observations have detected hydrogen signatures in Saturn's magnetosphere that correlate with Enceladus's orbital position, confirming theoretical predictions about hydrogen escape rates and spatial distribution. These measurements reveal that Enceladus contributes approximately 10^26 hydrogen atoms per second to Saturn's magnetospheric population, a flux that seems enormous by terrestrial standards, yet represents only a minuscule fraction of the Moon's total hydrogen inventory. Only took several billion years for this gentle but persistent atomic hemorrhaging to establish detectable hydrogen populations throughout Saturn's magnetic domain. The interaction between escaped hydrogen and Saturn's radiation environment creates feedback effects that influence the very processes responsible for hydrogen production. Some escaped atoms become ionized through collision with energetic electrons or photons, transforming them into protons that join the population of charged particles trapped within Saturn's magnetosphere. These newly created protons can subsequently bombard Enceladus's surface, participating in the radiolysis reactions that produce additional hydrogen atoms in a cycle that has persisted throughout the solar system's history. Temperature variations within Enceladus's ice introduce subtle but important effects on hydrogen escape efficiency. In the warmest regions near the south polar geysers, where temperatures may approach 90 Kelvin, thermal motion provides additional kinetic energy that can boost borderline velocity hydrogen atoms above the escape threshold. Conversely, the extreme cold of polar regions tends to thermalize hydrogen atoms more quickly, reducing their escape probability and creating spatial variations in hydrogen loss rates that correlate with surface temperature maps. The quantum mechanical behavior of hydrogen atoms at these extreme temperatures introduces phenomena that have no analogy in terrestrial experience. At 60 Kelvin, hydrogen atoms can exhibit wave-like properties that influence their interaction with the crystal lattice and their probability of escape from surface binding sites. Quantum tunneling effects allow some hydrogen atoms to penetrate energy barriers that would be insurmountable through classical thermal activation, creating escape pathways that operate even at temperatures approaching absolute zero. The preservation versus escape of hydrogen creates competing processes that determine the long-term evolution of Enceladus's surface chemistry. While radiation continuously produces new hydrogen atoms through water molecule dissociation, various trapping mechanisms can retain hydrogen within the ice matrix for extended periods. Hydrogen atoms may become incorporated into clathrate-like structures within the crystal lattice, or they may react with other radiolysis products to form more complex molecules that exhibit greater gravitational retention. The mystery of hydrogen isotope ratios in escaped atoms continues to challenge theoretical understanding. Different isotopes of hydrogen protium, deuterium, and tritium exhibit distinct escape probabilities due to their mass differences, but the detailed mechanisms that determine isotopic fractionation remain incompletely characterized. Laboratory experiments cannot adequately reproduce the combination of extreme cold, high vacuum, and continuous low-level bombardment that governs hydrogen behavior on Enceladus, leaving scientists to rely on theoretical models with significant uncertainties. Comparative studies with other icy satellites reveal that Enceladus exhibits remarkably efficient hydrogen escape compared to larger moons with stronger gravitational fields. Europa, despite experiencing similar radiation bombardment, retains a much larger fraction of its radiolytic hydrogen due to Jupiter's stronger tidal forces and the Moon's greater surface gravity. This difference highlights how planetary characteristics, particularly escape velocity and magnetic environment, influence the long-term chemical evolution of irradiated ice surfaces. The temporal variability of hydrogen escape rates reflects the complex dynamics of Saturn's magnetosphere and Enceladus's orbital mechanics. During periods of enhanced radiation bombardment, hydrogen production and escape rates increase proportionally, creating correlations between magnetospheric activity and hydrogen flux measurements. The Moon's 37-day orbital period introduces regular variations as different hemispheres alternately face the most intense radiation zones, establishing cyclical patterns in hydrogen escape that persist across geological timescales. Only took millions of years for hydrogen escape to establish equilibrium rates that balance production through radiolysis against loss to space and chemical incorporation into stable compounds. The irony of the lightest element becomes apparent: hydrogen. Fundamental to water and essential for life as humans understand it, proves least capable of remaining bound to the icy worlds where it might contribute to potentially habitable conditions. Between the quantum mechanics of molecular dissociation and the classical trajectories of ballistic escape, hydrogen atoms depart Enceladus with a persistence that gradually, but inexorably, alters the chemical composition of this distant world. Within the irradiated ice of Enceladus, molecules that would seem impossibly complex for such a sterile environment assemble themselves through the patient chemistry of radiation-induced synthesis. Carbon atoms, arriving as trace contaminants in meteoritic dust or emerging from the Moon's rocky interior, encounter the rich array of radiolysis products that permeate the frozen surface layers. Here, in temperatures so extreme that most chemical reactions proceed at geological pace, radiation provides the activation energy necessary to forge bonds between species that would never interact under purely thermal conditions. The formation of these complex molecules begins with the simplest possible precursors, individual atoms and radicals liberated from water molecules through particle bombardment, hydroxyl radicals, carrying unpaired electrons that make them highly reactive, can abstract hydrogen atoms from trace organic compounds or combine with carbon-bearing species to form alcohols and organic acids. Hydrogen atoms, freed from their molecular partnerships, readily add to carbon-carbon double bonds or participate in radical chain reactions that propagate through the ice matrix over distances measured in micrometers. The inventory of organic molecules detected on Enceladus through spacecraft observations includes species of surprising complexity for such an apparently lifeless world. Formaldehyde, the simplest aldehyde, forms readily when carbon monoxide itself, a product of radiolytic decomposition of carbon dioxide impurities, reacts with hydrogen atoms in the presence of radiation-induced catalytic sites. Methanol emerges through the sequential addition of hydrogen atoms to formaldehyde, while more complex alcohols can form through radical coupling reactions between organic fragments. The production of oxidants represents another category of radiation-induced chemistry that creates molecules with powerful chemical reactivity despite the extreme cold. Hydrogen peroxide, formed through the combination of hydroxyl radicals or the reaction of oxygen atoms with water molecules, accumulates in concentrations that can reach several percent by mass in heavily irradiated regions. Ozone, created when molecular oxygen encounters free oxygen atoms, remains stable in the frozen matrix while retaining its capacity for vigorous oxidation reactions when conditions permit. The spatial distribution of these complex molecules follows patterns that reflect both the radiation environment and the availability of precursor materials. Regions near impact craters, where meteoritic bombardment has delivered carbon-bearing compounds, exhibit enhanced concentrations of organic species created through subsequent radiation processing. The south polar regions, despite their geological activity that might be expected to destroy accumulated chemical products, show distinctive organic signatures that result from the interaction between radiation chemistry and the continuous supply of fresh ice from the interior. Temperature gradients within the ice create distinct chemical environments where different classes of molecules achieve stability. Near the surface, where temperatures remain constant at 60 Kelvin, most organic molecules become kinetically trapped in the configurations where radiation chemistry initially formed them. Deeper in the crust, where tidal heating and radioactive decay add fractional degrees of warmth, some molecules gain sufficient thermal energy to rearrange into more thermodynamically stable forms or to participate in secondary reactions with other accumulated products. The role of catalytic surfaces in promoting complex molecule formation adds another layer of sophistication to Enceladus's radiation chemistry. Mineral grains embedded within the ice, derived from the Moon's rocky core or delivered by meteorite bombardment, can serve as nucleation sites where organic molecules concentrate and react. These mineral surfaces can lower the activation barriers for certain reactions, allowing complex syntheses to proceed at rates that would be impossible in pure ice matrices. Recent theoretical models suggest that radiation-induced chemistry on Enceladus may produce molecules with sufficient complexity to serve as precursors for even more elaborate syntheses. Amino acid analogues molecules that share structural features with the building blocks of terrestrial proteins could potentially form through multi-step radical reactions involving carbon, nitrogen, and oxygen species. While such molecules would remain chemically distinct from biological amino acids, Their formation would demonstrate the capacity for radiation chemistry to generate sophisticated organic architectures in completely abiotic environments. The preservation of complex molecules within Enceladus's ice represents a remarkable example of chemical storage under extreme conditions. Unlike terrestrial environments, where organic molecules typically undergo rapid decomposition through oxidation, hydrolysis, or biological consumption, the pristine ice matrix of Enceladus provides exceptional chemical stability. Combined with the kinetic limitations imposed by extreme cold, this stability allows complex molecules to accumulate over geological timescales to concentrations that would be transient under more temperate conditions. The mystery of molecular complexity limits in radiation-driven systems continues to challenge theoretical understanding. While laboratory experiments have demonstrated the formation of relatively simple organic molecules under simulated Enceladus conditions, the synthesis of more complex species remains largely theoretical. The question of whether radiation chemistry alone can generate molecules of biological significance, or whether such complexity requires additional processes like hydrothermal chemistry or mineral catalysis, represents one of the most intriguing uncertainties in astrobiology. Only took millions of years for the current inventory of complex molecules to accumulate within Enceladus's most heavily irradiated regions. The irony of chemical sophistication in sterile environments becomes apparent this moon, which has never known life and exists in conditions that would be instantly lethal to terrestrial organisms, nonetheless generates molecular diversity that rivals some biological systems in its complexity and chemical richness. The temporal evolution of molecular complexity follows patterns that depend on both the continuous input of radiation energy and the gradual accumulation of precursor materials through meteoritic bombardment and interior processes. As radiation chemistry proceeds, the initially simple products serve as starting materials for increasingly complex syntheses, creating chemical networks that exhibit some characteristics of self-organization despite operating entirely through abiotic mechanisms. The distribution of complex molecules throughout the ice column creates a vertical zonation that reflects the interplay between radiation penetration, temperature gradients, and chemical stability. Surface layers contain the highest concentrations of recently formed molecules, while deeper regions preserve the accumulated products of millions of years of radiation chemistry. This chemical stratigraphy provides a record of Enceladus's radiation environment and its evolution over geological timescales. Between the quantum mechanics of radical formation and the thermodynamics of molecular stability, Enceladus maintains an inventory of complex chemical species that demonstrates the remarkable synthetic capacity of radiation-driven chemistry. Each molecule represents multiple successful encounters between reactive species, mediated by radiation energy and preserved by extreme cold, contributing to a chemical garden that flourishes in the absence of life while creating conditions that could potentially support more complex chemical evolution. The patience of chemical assembly in frozen time reveals itself through the gradual accumulation of molecular complexity across eons of steady bombardment. Only the most persistent reactions succeed in these extreme conditions, yet their products can persist indefinitely once formed, creating a chemical archive that preserves the signatures of radiation-induced synthesis across the entire history of the solar system. The energy budget of Enceladus receives contributions from sources both subtle and profound, with radiation bombardment adding its modest share to the thermal architecture that governs this distant moon's behavior. Each high-energy particle that strikes the ice surface deposits a fraction of its kinetic energy as heat, warming the frozen crust by immeasurable amounts that nonetheless accumulate over geological timescales to influence the moon's overall energy balance. This radiogenic heating operates alongside the much more substantial thermal contributions from tidal flexing and radioactive decay, yet it represents a persistent source of warmth that has operated continuously since Enceladus first formed within Saturn's magnetosphere. The thermodynamics of particle energy deposition follows patterns determined by the physics of collision cascades and electronic excitation within the ice crystal lattice. When a high-energy electron penetrates the surface, it transfers energy through inelastic collisions that initially appear as kinetic motion of displaced atoms and excited electronic states. This energy rapidly thermalizes through phonon interactions, quantized vibrations of the crystal lattice that represent heat at the atomic level. The process occurs within picoseconds of the initial particle impact, converting the ordered kinetic energy of the bombarding particle into the random thermal motion that characterizes temperature. The spatial distribution of radiogenic heating reflects the penetration characteristics of different radiation types and the three-dimensional structure of Saturn's magnetosphere. High-energy electrons deposit their energy relatively uniformly throughout their range, typically extending several centimeters into the ice surface and creating broad zones of enhanced thermal input. Protons, carrying greater kinetic energy due to their superior mass, can penetrate meters into the crust while depositing energy along dense tracks that follow their trajectories through the ice matrix. The cumulative effect creates temperature gradients that vary with depth and location according to the local radiation environment. Quantitative estimates of radiation heating rates require careful consideration of particle fluxes, energy spectra, and energy deposition efficiencies throughout Enceladus's radiation environment. Current models suggest that radiation bombardment delivers approximately 10⁴ watts per square meter to the Moon's surface, a power density that seems negligible compared to solar heating on terrestrial worlds, yet becomes significant when integrated over Enceladus's entire surface area and compared to other heat sources available to this small, distant moon. Only took billions of years for this gentle warming to establish its role in the complex thermal evolution of Enceladus's ice shell. The relationship between radiation heating and other thermal processes operating within Enceladus reveals interesting scales of comparison. Tidal heating, driven by the gravitational interaction between Enceladus, Saturn, and the other major satellites, provides the dominant thermal input that powers the Moon's geological activity and maintains its subsurface ocean. Radiogenic heating from the decay of long-lived isotopes within the rocky core contributes additional warmth that has operated since the solar system's formation. Radiation heating, while smaller in magnitude than these other sources, operates continuously and uniformly across the entire surface, providing a baseline thermal input that supplements the more variable contributions from tidal and radiogenic processes. The temporal variations in radiation heating follow the complex dynamics of Saturn's magnetosphere and Enceladus's orbital mechanics. During periods when the magnetosphere contracts due to enhanced solar wind pressure, increased particle fluxes deliver greater thermal energy to the Moon's surface. The Moon's orbital eccentricity introduces additional variations as Enceladus alternately approaches and recedes from Saturn, experiencing changing tidal forces that influence both the radiation environment and the efficiency of tidal heating processes. The efficiency of thermal conduction within Enceladus's ice shell determines how radiation-deposited heat influences subsurface temperatures and geological processes. Pure water ice at the temperatures found on Enceladus exhibits thermal conductivity values that allow heat to diffuse significant distances before radiating away to space. This efficient heat transport means that radiation heating at the surface can contribute to warming deeper layers of the ice shell, potentially influencing the mechanical properties of the crust and its response to tidal stresses. Recent theoretical models have explored the possibility that radiation heating could create feedback effects that amplify its thermal contributions under certain conditions. As radiation heats the ice, it may enhance the mobility of chemical species and defects within the crystal lattice, potentially accelerating certain radiation-induced reactions that release additional heat. These feedback mechanisms remain speculative due to the difficulty of reproducing Enceladus conditions in laboratory experiments, yet they represent intriguing possibilities for coupling between radiation chemistry and thermal evolution. The role of radiation heating in driving sublimation processes at Enceladus's surface introduces additional complexity into the thermal budget calculations. When radiation energy raises local temperatures sufficiently to drive water molecules from the solid directly to the vapor phase, the latent heat of sublimation creates cooling effects that partially offset the warming from energy deposition. This creates local thermal equilibria that depend on the balance between radiation input, sublimation cooling, and heat conduction to surrounding regions. The mystery of thermal coupling between surface radiation heating and deep subsurface processes continues to challenge scientific understanding. While the direct thermal contribution of radiation heating remains small compared to tidal heating, some theoretical models suggest that surface heating could influence convection patterns within the ice shell or affect the stability of the subsurface ocean. These potential coupling mechanisms remain highly speculative, yet they highlight the interconnected nature of thermal processes operating within icy satellites. Comparative studies with other radiation-bombarded moons reveal that Enceladus experiences relatively modest radiation heating compared to satellites closer to their parent planets. Europa, orbiting deep within Jupiter's intense radiation environment, receives radiation heating rates that exceed Enceladus values by orders of magnitude. This difference reflects both the greater intensity of Jupiter's magnetosphere and Europa's closer proximity to intense radiation belts, demonstrating how planetary characteristics influence the thermal evolution of their satellite systems. The seasonal and diurnal variations in radiation heating remain minimal due to Enceladus's synchronous rotation and the relatively stable configuration of Saturn's magnetosphere. Unlike terrestrial worlds where solar heating creates dramatic temperature cycles, radiation heating on Enceladus operates with remarkable consistency, providing steady thermal input that varies only in response to magnetospheric dynamics and orbital mechanics rather than seasonal or daily cycles. Only took millions of orbital periods for radiation heating to establish its current patterns of energy deposition across Enceladus's surface. The irony of cosmic warmth becomes apparent this moon, so distant from the Sun that solar heating contributes virtually nothing to its thermal budget, receives measurable warming from the very radiation environment that creates chemical violence throughout its ice shell. Between the quantum scale of individual energy deposition events and the global consequences of accumulated thermal input, radiation heating contributes its modest share to the complex thermal architecture that enables Enceladus to maintain geological activity and potentially habitable conditions within its hidden ocean. The patience of thermal accumulation reveals itself through the gradual warming effects that operate across geological timescales, adding infinitesimal amounts of heat with each particle impact, yet contributing to the overall energy balance that determines whether ice remains frozen or achieves the mobility necessary for geological processes and chemical evolution. Above the tiger stripes of Enceladus's south polar region, towering geysers of water vapor create ephemeral atmospheric shields that temporarily reduce the relentless bombardment of high-energy particles across localized regions of the moon's surface. These plumes, rising hundreds of kilometers into the vacuum of space before dispersing into Saturn's E-ring, represent one of the most dynamic geological phenomena in the outer solar system. Yet their interaction with the radiation environment reveals subtle protective effects that operate on timescales ranging from hours to decades, creating chemical oases where the accumulated damage from particle bombardment proceeds at slightly reduced rates compared to the exposed planes that surround them. The physics of radiation shielding by tenuous atmospheres follows principles that seem almost counterintuitive given the extreme thinness of Enceladus's geyser plumes. The water vapor density within these plumes reaches maximum values of only 10^12 molecules per cubic centimeter, approximately 1 trillion times less dense than Earth's atmosphere at sea level. Yet even this gossamer-thin material provides measurable attenuation of incident radiation, particularly for lower energy particles that can be scattered or absorbed through collisions with water molecules in the vapor phase. The geometry of geyser-induced shielding creates complex three-dimensional patterns that vary with wind conditions, eruption intensity, and the temporal behavior of individual vents along the tiger stripe fractures. Each geyser creates a roughly conical zone of reduced particle flux extending downwind from the eruption site, with shielding effectiveness decreasing with distance as the vapor plume disperses and thins. The overlapping protection zones from multiple active geysers create a patchwork of varying radiation exposure levels across the South Polar region, establishing chemical gradients that reflect both the intensity and duration of local volcanic activity. The temporal variations in geyser activity introduce corresponding fluctuations in radiation shielding effectiveness that operate across multiple timescales. Individual eruption events may last for hours or days, providing temporary respite from bombardment followed by renewed exposure as volcanic activity wanes. Longer-term variations in geyser intensity, potentially linked to tidal cycles and orbital mechanics, create periodic changes in shielding patterns that could influence the long-term accumulation of radiation damage across the South Polar terrain. The selectivity of atmospheric shielding becomes apparent when considering how different types of radiation interact with water vapor molecules. Low-energy electrons, with kinetic energies measured in hundreds of electron volts, can be efficiently scattered or absorbed by collisions with water molecules, creating significant reductions in flux within geyser plumes. Higher energy protons and electrons penetrate the tenuous atmosphere with minimal attenuation, maintaining their full bombardment intensity even within the densest portions of active plumes. This selectivity means that atmospheric shielding preferentially protects against certain types of radiation damage while leaving other processes largely unaffected. Chemical reactions within the geyser plumes themselves create additional complexity in the shielding process. Water vapor molecules can undergo radiolysis when struck by high-energy particles, producing the same hydroxyl radicals, hydrogen atoms, and molecular oxygen that form within the solid ice. However, the gas phase chemistry proceeds through different reaction pathways and at different rates compared to solid-state processes, potentially creating unique chemical signatures within the plume environment that differ from surface radiation chemistry products. The deposition of plume material onto surrounding surface areas creates localized zones where fresh, unirradiated ice covers previously bombarded terrain. This resurfacing process, operating continuously wherever geyser activity persists, effectively resets the radiation damage clock by burying accumulated chemical modifications beneath layers of pristine water ice. The thickness of these deposits varies with distance from active vents and the duration of volcanic activity, creating topographic and chemical variations that record the history of South Polar geological processes. Recent spacecraft observations have detected correlations between geyser activity and local variations in surface composition that suggest measurable shielding effects on radiation chemistry. Regions within the influence of active plumes show reduced concentrations of hydrogen peroxide and other radiolysis products compared to areas outside plume coverage, though the effects remain subtle due to the limited duration and intensity of atmospheric protection. Only took decades of continuous geyser activity to establish these chemical gradients, yet they demonstrate the capacity for geological processes to influence radiation environments on planetary scales. The interaction between escaping plume material and the ambient radiation field creates feedback effects that influence both atmospheric dynamics and bombardment patterns. Water molecules ejected from geysers can become ionized through collisions with high-energy particles, creating charged species that respond to Saturn's magnetic field and contribute to the local plasma environment. These newly ionized molecules may follow complex trajectories that eventually lead them back to Enceladus's surface, creating indirect pathways for material transport between different regions of the Moon. The mystery of plume composition and its influence on shielding effectiveness continues to evolve as new observations reveal unexpected chemical complexity within Enceladus's geysers. Recent detections of organic molecules, salts, and silicate particles within plume material suggest that the volcanic activity taps into chemical reservoirs that include more than pure water ice. These additional components may enhance or modify the radiation shielding properties of geyser plumes while contributing their own distinctive signatures to local radiation chemistry processes. The preservation of shielding signatures in surface materials provides indirect evidence for the long-term effectiveness of atmospheric protection. Chemical mapping of the South Polar region reveals patterns that correlate with current geyser locations, suggesting that plume-induced shielding has operated consistently enough to create detectable modifications in surface composition. These correlations must be interpreted carefully. However, since the same geological processes that drive geyser activity also contribute to surface renewal through the deposition of fresh ice, the comparative context of atmospheric shielding on other icy satellites reveals that Enceladus's geyser plumes represent a relatively rare phenomenon in the outer solar system. Most radiation-bombarded moons lack significant atmospheric protection, exposing their surfaces to the full intensity of magnetospheric bombardment throughout their geological history. Europa's tenuous oxygen atmosphere provides minimal shielding compared to Enceladus's water vapor plumes, while Io's dense volcanic atmosphere creates much more substantial protection against Jupiter's intense radiation environment. Only took millions of years for the current patterns of geyser-induced shielding to establish themselves within Enceladus's South Polar region. The irony of geological protection becomes apparent. The same internal processes that drive Enceladus's remarkable geological activity also create the only significant natural defense against the radiation bombardment that continuously modifies the Moon's surface chemistry. Between the quantum mechanics of particle scattering and the fluid dynamics of geyser eruptions, atmospheric shielding provides temporary sanctuaries where radiation damage accumulates at reduced rates, creating chemical heterogeneities that record the complex interplay between geological activity and space weathering processes. The ephemeral nature of this protection reveals itself in the constant flux of plume activity, with shielding effectiveness waxing and waning according to the geological rhythms that govern Enceladus's internal dynamics. Beneath the surface of Enceladus, layers of ice preserve a stratigraphic library that records the evolution of radiation bombardment across geological timescales, with the precision of tree rings documenting terrestrial climate variations. Each stratum within the frozen crust contains chemical signatures that reflect the radiation environment prevailing when that particular layer first solidified from liquid water or accumulated through surface processes. The deepest accessible ice, potentially dating back hundreds of millions of years, holds molecular testimony to ancient magnetospheric conditions that may have differed substantially from the radiation patterns that characterize the contemporary Saturnian system. The formation of this chemical stratigraphy occurs through multiple processes that operate simultaneously across different depth scales within Enceladus's ice shell. Surface accumulation of radiation damage creates the uppermost layers, where the most recent bombardment history remains recorded in the concentrations and distributions of radiolysis products. Deeper within the crust. Ancient ice preserves the chemical signatures of radiation exposure that occurred when those layers occupied surface positions, before subsequent geological processes buried them beneath newer material deposited through volcanic activity or impact gardening. The preservation of radiation signatures depends critically on the thermal history and mechanical deformation experienced by ice at various depths within the crust. Near surface layers, maintained at temperatures around 60 Kelvin throughout their exposure history, retain chemical modifications with remarkable fidelity over geological timescales. Deeper ice, subjected to gradual warming through tidal heating and radioactive decay, may experience partial annealing of radiation damage as increased molecular mobility allows some chemical species to migrate, react, or decompose according to thermodynamic rather than purely kinetic constraints. The vertical distribution of different radiolysis products creates distinctive chemical profiles that vary with depth in patterns that reflect both the initial conditions of formation and subsequent modification through thermal and mechanical processes. Hydrogen peroxide, relatively stable under extreme cold conditions, tends to preserve its original concentration profiles with minimal vertical migration. Molecular oxygen, being less chemically reactive, can persist at depth for extended periods while gradually redistributing through diffusion processes that operate on million-year timescales. The influence of Saturn's magnetic field evolution on the radiation archive within Enceladus's ice introduces temporal variations that span the entire history of the solar system. Theoretical models suggest that Saturn's magnetosphere has undergone significant changes in intensity and configuration as the planet evolved. The satellite system migrated outward through tidal interactions, and the solar wind environment varied in response to the Sun's changing luminosity and magnetic activity. These magnetospheric variations would have created corresponding changes in the radiation environment experienced by Enceladus, leaving signatures that remain preserved in the ice column. Recent analysis of the chemical gradients observed in Enceladus's surface materials suggests that radiation bombardment rates may have varied by factors of 2 to 5 over the past billion years, based on the depth-dependent concentrations of long-lived radiolysis products and their spatial distributions across different geological units. These variations could result from changes in Saturn's magnetic field strength, modifications in the satellite's orbital characteristics, or long-term evolution in the solar wind environment that drives magnetospheric dynamics throughout the outer solar system. The role of geological processes in modifying or destroying the radiation archive adds complexity to interpretations of the chemical stratigraphy. Tidal heating creates convection patterns within the ice shell that can transport material vertically over distances of kilometers, potentially mixing ice layers that formed under different radiation conditions. The formation and evolution of fracture systems like the tiger stripes can expose deep ice to renewed radiation bombardment, creating complex overprinting relationships between ancient and recent chemical modifications. The detection of isotopic variations within Enceladus's ice provides additional constraints on the radiation history preserved in different stratigraphic levels. Cosmic ray bombardment produces distinctive isotopic signatures through nuclear spallation reactions that create rare isotopes not found in primordial solar system materials. The vertical distribution of these cosmogenic isotopes within the ice column should reflect the integrated cosmic ray exposure experienced by different layers, providing independent verification of radiation exposure histories inferred from chemical analysis. The mystery of chemical stability over geological timescales continues to challenge understanding of how radiation signatures can persist within dynamically evolving ice shells. Laboratory experiments cannot adequately reproduce the combination of extreme cold, mechanical stress, and chemical isolation that characterizes conditions within Enceladus's crust, leaving scientists to extrapolate from limited data to predict preservation mechanisms operating over millions of years. Computer simulations suggest that some radiation products could remain stable for geological time periods, while others might undergo continuous modification through slow chemical evolution. Comparative studies with terrestrial ice archives, such as those preserved in polar ice sheets and glacial deposits, provide limited analogy for understanding preservation mechanisms in extraterrestrial environments. Earth's ice records document atmospheric and climatic variations over timescales of hundreds of thousands of years. Yet the chemical and physical processes operating within these terrestrial archives differ substantially from the radiation-dominated environments that characterize icy satellites in the outer solar system. Only took hundreds of millions of years for the current chemical stratigraphy within Enceladus's ice shell to accumulate. Yet this archive may contain information spanning the entire age of the solar system if the deepest ice layers have remained preserved since the Moon's initial formation. The irony of chemical memory in frozen time becomes apparent. Ice, which seems so ephemeral and changeable in terrestrial experience, provides one of the most stable and persistent recording media available for documenting planetary environmental conditions across geological history. The spatial variations in stratigraphic preservation across Enceladus's surface create a complex three-dimensional archive where different locations preserve different aspects of the Moon's radiation history. Regions with active geology experience continuous surface renewal that limits the depth and completeness of preserved records, while tectonically quiet areas may retain stratigraphic sequences extending back to the earliest periods of bombardment history. Between the molecular precision of individual chemical modifications and the global patterns of magnetospheric evolution, Enceladus's ice column preserves a library of radiation history that rivals the geological record of terrestrial planets in its scope and detail. Each chemical signature represents successful preservation across timescales that challenge human comprehension, creating archives that could eventually reveal the environmental history of the outer solar system with unprecedented temporal resolution and chemical specificity. The patience of chemical preservation reveals itself through the maintenance of molecular information across eons of geological change, with ancient bombardment signatures persisting alongside evidence of continuing radiation exposure in a complex palimpsest of chemical history written in the language of atomic arrangements and molecular abundances. Within the chemical laboratories of Enceladus's irradiated ice, radiation-induced reactions create not merely random destruction, but rather systematic construction of molecular architectures that could serve as foundation stones for even more complex chemical evolution. The hydroxyl radicals, hydrogen atoms, and molecular fragments generated through initial radiolysis events represent reactive building blocks that can combine in countless permutations to construct molecules of increasing sophistication and chemical potential. These radiation-synthesized compounds, preserved in the extreme cold like specimens in some cosmic museum, await future interactions that might unlock pathways toward chemical complexity that approaches though never achieves the organizational principles observed in living systems. The concept of molecular scaffolding emerges when examining how radiation chemistry creates structural frameworks that facilitate subsequent synthetic reactions. Simple aldehydes and alcohols, formed through primary radiolysis processes, can serve as attachment points where additional functional groups accumulate through secondary reactions. Formaldehyde molecules, generated when trace carbon monoxide reacts with radiation-produced hydrogen atoms, provide reactive sites where additional carbon-bearing fragments can attach to form longer-chain compounds. These growing molecular structures create increasingly complex architectures while maintaining the chemical reactivity necessary for continued synthetic evolution. The formation of oxidizing environments through radiolytic oxygen production creates chemical conditions that would be impossible to achieve through purely thermal processes at Enceladus's surface temperatures. Hydrogen peroxide concentrations reaching several percent by mass establish strongly oxidizing conditions that could drive synthetic reactions between organic molecules and mineral components delivered through meteoritic bombardment. These reactions, proceeding slowly but persistently over geological timescales, could generate molecular complexity that exceeds anything achievable through radiation chemistry alone. The role of mineral catalysis in enhancing radiation-driven synthesis introduces possibilities for chemical evolution that extend far beyond the limitations of pure ice chemistry. Silicate grains and metallic particles, derived from Enceladus's rocky core or delivered by micrometeorite bombardment, can serve as catalytic surfaces where organic molecules concentrate and react under conditions that would not support similar reactions in homogeneous ice matrices. These mineral surfaces can lower activation barriers, orient reactive molecules in favorable geometries, and provide electron transfer pathways that enable synthetic reactions impossible in purely organic systems. The spatial organization of chemical microenvironments within the irradiated ice creates zones where different classes of synthetic reactions can proceed simultaneously without mutual interference. Regions enriched in hydrogen peroxide support oxidative chemistry that generates oxygenated organic compounds, while areas with high concentrations of molecular hydrogen favor reductive reactions that create saturated hydrocarbons. The coexistence of these contrasting chemical environments within the same ice mass enables synthetic pathways that would be mutually exclusive in homogeneous chemical systems. The temporal evolution of molecular complexity follows patterns that suggest systematic progression from simple to sophisticated chemical architectures. Initial radiation chemistry generates the basic building blocks. Formaldehyde, methanol, hydrogen peroxide within thousands of years of bombardment initiation. Secondary reactions between these primary products create more complex species, organic acids, simple sugars, amino acid analogues over timescales of millions of years, tertiary synthetic pathways, involving reactions between accumulated secondary products, could potentially generate molecular complexity that approaches biological levels of sophistication over geological time periods. Recent theoretical models have explored whether radiation-driven chemistry on Enceladus could generate molecules with catalytic properties, compounds capable of accelerating chemical reactions beyond their own formation and destruction. Such autocatalytic systems would represent a crucial step toward the kind of self-organizing chemistry that characterizes living systems, though they would emerge through purely abiotic processes operating under extreme conditions. The formation of even simple autocatalytic networks would transform Enceladus's ice from a passive repository of radiation products into an active chemical system capable of evolutionary behavior. The possibility of information storage and transfer through chemical means introduces speculative but intriguing possibilities for molecular evolution within irradiated ice systems. Complex organic molecules can exhibit stereochemical properties, three-dimensional arrangements of atoms that influence chemical reactivity and molecular recognition. If radiation-driven synthesis could generate molecules with specific stereochemical signatures, these could serve as templates that bias subsequent synthetic reactions toward particular products, creating primitive inheritance mechanisms that operate through purely chemical rather than biological processes. The preservation of synthetic potential within Enceladus's ice creates a chemical inventory that could respond dramatically to environmental changes that alter reaction conditions. If future geological processes were to warm portions of the ice shell, increase chemical mobility, or provide new catalytic surfaces. The accumulated products of billions of years of radiation chemistry could undergo explosive synthetic evolution that rapidly generates molecular complexity approaching biological levels. This chemical potential energy, stored in the form of reactive molecules and oxidizing conditions, represents a form of planetary-scale chemical battery that awaits activation. The mystery of complexity, limits in abiotic synthetic systems, continues to challenge understanding of how far chemical evolution can proceed without the organizing principles provided by living systems. While laboratory experiments have demonstrated the formation of simple organic molecules under simulated space conditions, the synthesis of truly complex molecular architectures, proteins, nucleic acids, complex lipids remains largely theoretical. The question of whether purely chemical processes can generate functional molecular machines comparable to biological systems represents one of the deepest questions in astrobiology. Only took billions of years for the current inventory of synthetic precursors to accumulate within Enceladus's most chemically active regions. The irony of potential without activation becomes apparent. This moon possesses chemical conditions that could potentially support remarkably sophisticated synthetic evolution, yet lacks the energy sources and catalytic systems necessary to fully realize this potential. The extreme cold that preserves accumulated chemical complexity also prevents the molecular mobility necessary for advanced synthetic reactions to proceed at appreciable rates. The comparative context of chemical evolution on other worlds reveals that Enceladus occupies a unique position in the spectrum of planetary chemical environments. Unlike Mars or Europa, where chemical evolution must compete with destructive processes that limit molecular accumulation, Enceladus combines chemical productivity through radiation synthesis with exceptional preservation conditions that allow complex molecules to survive for geological periods. This combination creates conditions that may be uniquely favorable for the development of sophisticated abiotic chemistry. Between the quantum mechanics of radical formation and the thermodynamics of molecular stability, Enceladus maintains conditions that could potentially support chemical evolution toward unprecedented levels of molecular complexity. Each synthetic reaction represents a step toward greater chemical sophistication, building molecular architectures that await future conditions that might unlock their full synthetic potential and transform this frozen world into an active center of chemical evolution. The architecture of possibility reveals itself through the patient accumulation of reactive molecules and oxidizing conditions across geological time, creating chemical foundations that could support sophisticated synthetic evolution if future environmental changes provide the activation energy necessary to realize the full potential of this radiation-driven chemistry. The eccentric orbit of Enceladus, stretching and compressing across its 37-day journey around Saturn, creates rhythmic variations in the radiation bombardment that bathes the moon's frozen surface with the regularity of a cosmic metronome. This orbital dance, driven by gravitational interactions with Saturn and the neighboring moons Mimas and Dione, generates periodic changes in Enceladus's distance from its parent planet that translate directly into corresponding fluctuations in magnetospheric radiation exposure. The Moon alternately approaches within 237,000 kilometers of Saturn at periapsis, before receding to 239,000 kilometers, at apoapsis, a modest variation of less than 1%, that nonetheless creates measurable cycles in the intensity and composition of particle bombardment. The physics underlying these orbital radiation cycles reflects the complex three-dimensional structure of Saturn's magnetosphere and how charged particle populations vary with radial distance from the planet. Closer to Saturn, magnetic field lines converge and particle densities increase, creating more intense radiation environments that deliver higher fluxes of energetic electrons and protons to any satellite that ventures into these regions. Further from the planet, the magnetosphere expands and particle populations dilute, providing relative respites from bombardment that allow previously accumulated radiation damage to evolve through thermal and chemical processes operating at reduced interference levels. The temporal signature of these radiation cycles manifests across multiple overlapping periodicities that reflect both Enceladus's orbital mechanics and Saturn's rotational dynamics. The primary 1-1 37-day orbital period creates the fundamental rhythm of radiation variation as Enceladus moves through different magnetospheric zones. Saturn's 10.7-hour rotation period introduces shorter-term fluctuations as the planet's tilted magnetic field sweeps patterns of enhanced and depleted particle flux past the Moon's orbital position. Longer-term variations occur as Enceladus's orbital eccentricity itself undergoes slow changes driven by tidal evolution and gravitational perturbations from other satellites. The chemical consequences of rhythmic bombardment create distinctive signatures within the radiolysis products that accumulate across Enceladus's surface. During periods of intense radiation exposure near periapsis, radiolysis proceeds at accelerated rates that favor certain chemical pathways over others, potentially creating enhanced concentrations of highly reactive species like hydroxyl radicals and atomic oxygen. The reduced bombardment rates near apoapsis allow these reactive intermediates to participate in secondary reactions that might be suppressed during high-intensity bombardment periods, creating chemical products that reflect the cyclical nature of the radiation environment. The spatial distribution of orbital radiation effects varies across Enceladus's surface according to the orientation and geometry of Saturn's magnetic field relative to the Moon's orbital plane. The leading hemisphere, which faces forward into the magnetospheric particle flow during orbital motion, experiences the most pronounced variations in bombardment intensity as Enceladus moves between periapsis and apoapsis. The trailing hemisphere exhibits more subdued cyclical variations, though even there, the orbital modulation of radiation exposure creates detectable patterns in surface chemistry and coloration. Recent computer simulations have revealed that the orbital radiation cycles can create resonance effects with certain chemical processes operating within the irradiated ice. Reactions with characteristic timescales that match or harmonically relate to the orbital period may become synchronized with the bombardment cycles, leading to enhanced production of specific radiolysis products during particular phases of Enceladus's orbit. These resonance phenomena could amplify the chemical signatures of orbital variation beyond what simple linear scaling with radiation intensity would predict. The preservation of orbital cycle signatures in the accumulated radiation damage record requires chemical processes with memory timescales comparable to or longer than the orbital period. Molecular species with lifetimes of days to weeks could exhibit concentration fluctuations that directly track the orbital bombardment cycles, creating chemical oscillations that persist as long as the molecules themselves remain stable. Longer-lived species with geological persistence times would integrate over many orbital cycles, preserving only the long-term average effects while losing information about short-term orbital variations. The interaction between orbital radiation cycles and other periodic processes operating on Enceladus introduces potential for complex beating patterns and interference effects in the chemical evolution of the surface. Tidal heating also varies with orbital period, creating thermal cycles that could interact with radiation chemistry to produce combined effects that differ from either process operating independently. The tiger stripe geysers show evidence of tidal modulation in their eruption timing, potentially creating correlations between atmospheric shielding effectiveness and orbital radiation cycles. The mystery of long-term orbital evolution and its influence on radiation patterns adds another temporal dimension to understanding Enceladus's chemical history. Theoretical models suggest that the Moon's orbit may have migrated outward from Saturn over geological timescales due to tidal interactions, carrying it through different radiation environments as the orbital radius gradually increased. Ancient ice layers preserved within the crust could contain chemical signatures that record these historical changes in orbital characteristics and their corresponding influence on radiation bombardment patterns. The detectability of orbital radiation signatures through remote sensing observations remains challenging due to the subtle nature of the chemical variations and the limited spatial and temporal resolution available from spacecraft instruments. Future missions with enhanced sensitivity and longer observation periods might be able to detect chemical oscillations that correlate with orbital mechanics, providing direct confirmation of the theoretical predictions about rhythmic bombardment effects on surface chemistry. Only took millions of orbital revolutions for the current patterns of cyclical bombardment to establish their signatures within Enceladus's surface materials. The irony of cosmic clockwork becomes apparent this moon, so distant that solar radiation provides negligible heating. Nonetheless, experiences precise temporal rhythms in its radiation environment that operate with the regularity of planetary motion and the persistence of celestial mechanics. The gravitational dance that shapes Enceladus's orbit also modulates the invisible violence that continuously modifies its chemical composition. The measurement of chemical periodicity within irradiated materials could potentially provide independent constraints on Enceladus's orbital history and the evolution of Saturn's magnetosphere over geological timescales. Chemical species with known radiation production rates and decay characteristics could serve as chronometers that record the timing and intensity of past bombardment episodes, creating temporal calibration systems based on molecular rather than isotopic decay processes. Between the precision of orbital mechanics and the stochastic nature of individual particle impacts, Enceladus experiences radiation bombardment that combines deterministic periodicity with quantum-scale randomness. Each orbital cycle delivers statistically predictable numbers of particle impacts while maintaining unpredictability in the timing and location of individual collision events, creating chemical evolution that proceeds according to both clockwork regularity and random molecular encounters. The rhythm of bombardment reveals itself through the patient accumulation of cyclical chemical signatures across geological time, establishing temporal patterns in molecular damage and synthesis that reflect the gravitational choreography of the Saturnian satellite system and its continuous interaction with the planet's invisible magnetic architecture. In the vast spaces between particle impacts, where femtoseconds stretch into geological epochs and quantum-scale violence gives way to molecular stillness, the ice crystals of Enceladus rest in formation so perfect they approach the theoretical limits of crystalline order. These intervals of quiet, measured not in human time but in the patient rhythms of atomic arrangement and interstellar silence, encompass the majority of existence for any given water molecule within the frozen crust. Between the arrival of one high-energy particle and the next, millions of years may pass during which individual molecules maintain their positions with mathematical precision, their hydrogen bonds locked in hexagonal geometries that have persisted since the ice first solidified from primordial vapor. The mathematics of particle bombardment reveal the profound nature of this molecular patience. With approximately 10 billion impacts per square centimeter per second across Enceladus's entire surface, the average spacing between impact sites measures roughly 10 nanometers, approximately 30 times the diameter of a single water molecule. This seemingly dense bombardment pattern creates a landscape of violence when viewed at appropriate scales, yet from the perspective of individual molecules, each impact affects only a tiny fraction of the surrounding crystalline matrix, while leaving vast regions untouched for periods that exceed the age of complex life on Earth. The quantum mechanics of molecular stability in perfect crystals operates according to principles that seem almost timeless compared to the dynamic processes that characterize most planetary environments. At the 60 Kelvin temperatures that govern Enceladus's surface, thermal motion slows to levels where molecular vibrations barely disturb the crystalline lattice. Water molecules occupy their assigned positions with positional uncertainties measured in fractions of angstroms, creating ordered arrangements that approach the absolute zero limit of perfect crystalline structure. Only the occasional quantum fluctuation, or lattice phonon, disturbs this near-perfect stillness. The preservation of chemical information within these quiet zones creates archives of molecular memory that span geological timescales with remarkable fidelity. Radiation-induced defects, once formed through particle bombardment, remain kinetically trapped in their modified configurations for periods that could extend throughout the remaining lifetime of the solar system. The extreme cold prevents thermal annealing processes that would normally allow damaged crystal structures to heal, creating permanent records of every significant radiation event that has affected each microscopic region of the ice. The spatial distribution of undamaged regions within the ice matrix creates a complex three-dimensional network of pristine crystalline domains separated by zones of accumulated radiation damage. Computer simulations suggest that these undamaged regions may constitute a significant fraction of the total ice volume, particularly in deeper layers where only the most energetic particles can penetrate. These pristine zones serve as reference standards that preserve the original chemical and isotopic composition of Enceladus's ice, providing baselines for measuring the cumulative effects of radiation bombardment. The chemical isolation of molecules within perfect crystal lattices creates conditions where individual water molecules can persist in their original configurations for periods that approach the age of the solar system. Unlike terrestrial ice, which undergoes continuous recrystallization and chemical exchange with atmospheric water vapor, the ice of Enceladus exists in near-perfect isolation from chemical interaction. Each molecule becomes a time capsule, preserving the isotopic signatures and molecular arrangements that characterized the protoplanetary disk from which the Saturnian system originally condensed. The role of quantum tunneling in maintaining long-term stability introduces subtle but important effects that operate over geological timescales. Even at temperatures approaching absolute zero, quantum mechanical effects allow certain atomic rearrangements to occur through tunneling processes that bypass classical energy barriers. These quantum effects proceed at rates so slow they become measurable only over millions of years, creating gradual evolution in crystal structure that represents one of the most patient forms of chemical change operating in the solar system. The acoustic properties of perfect ice crystals create conditions where mechanical vibrations can propagate over considerable distances without significant damping. Sound waves generated by radiation impacts or thermal expansion could potentially travel through the crystalline matrix for kilometers before dissipating, creating a form of mechanical communication between different regions of the ice shell. These acoustic signals, operating at frequencies far below human perception, represent another dimension of information transfer within the apparently static, frozen world. The optical properties of undamaged ice regions maintain the exceptional transparency and reflectivity that characterize Enceladus's surface when observed from great distances. Light penetrating into the crystal lattice can travel significant depths before encountering scattering centers or absorption sites, creating internal illumination effects that might influence photochemical processes within the ice matrix. The high albedo that makes Enceladus one of the most reflective objects in the solar system results directly from the optical perfection of these undamaged crystalline domains. The mystery of information preservation over cosmic timescales continues to challenge understanding of how molecular arrangements can maintain their integrity across geological epochs. The combination of extreme cold, chemical isolation, and mechanical stability creates conditions that have no terrestrial analog, requiring theoretical frameworks that extend far beyond conventional chemical kinetics and thermodynamics. Some theoretical models suggest that information encoded in crystalline arrangements could persist for billions of years. Creating molecular libraries that preserve records of solar system formation and early planetary evolution only took billions of years for the current distribution of damaged and undamaged regions to establish itself within Enceladus's ice shell. Yet the preservation timescales for information within pristine crystalline domains could extend far into the future, potentially surviving the evolution of Saturn into a red giant star and the eventual migration of the satellite system to larger orbital distances. The irony of permanence in apparent fragility becomes evident. Water ice, so ephemeral in terrestrial experience, provides one of the most stable and persistent information storage media available in the cosmos. The vastness of unaffected space within the crystal lattice reveals itself through statistical analysis of bombardment patterns and damage distributions. Between the discrete violence of individual particle impacts and the global accumulation of chemical modifications, enormous volumes of ice remain in configurations indistinguishable from their primordial arrangements, creating molecular museums that preserve the chemical signatures of solar system formation within crystalline matrices of extraordinary stability and longevity. The patience of molecular arrangement expresses itself through the maintenance of perfect geometric relationships across timescales that challenge human comprehension, with individual water molecules maintaining their designated positions in hexagonal lattices, while cosmic evolution proceeds around them at scales ranging from planetary to galactic, creating islands of stability within the dynamic universe that surrounds them. Between these rare moments of cosmic violence and the eternal stillness that separates them, ice crystals on Enceladus preserve their molecular memories in formations so perfect they could serve as standards for crystalline order throughout the galaxy, waiting in patient quiet for the next particle impact while maintaining their chemical testimony to the invisible forces that shape worlds in the outer reaches of the solar system. The radiation that shapes Enceladus continues its patient work in the deepest silences of space, where time moves according to rhythms that dwarf human perception and molecular changes accumulate across eons with the inevitability of astronomical mechanics. Each particle impact, invisible and instantaneous, contributes to transformations that will outlast the geological evolution of Earth and persist into futures where the Sun itself has begun its final stellar metamorphosis. The ice remembers every collision in its crystalline matrix, preserving molecular testimony to cosmic violence in structures so stable they approach permanence. In the spaces between bombardment events, where quantum stillness extends across periods measured in millions of years, water molecules rest in configurations that have remained unchanged since the early epochs of planetary formation. These intervals of perfect order, vastly more extensive than the damaged zones created by radiation, constitute the majority of Enceladus's frozen existence. Here, in lattices of mathematical precision, the Moon preserves its original chemical heritage while slowly accumulating the subtle modifications that cosmic radiation writes across its surface, one atom at a time. The chemical gardens that flourish in this sterile environment demonstrate the universe's capacity for creating complexity through the simplest possible mechanisms: energetic particles, frozen water, and time periods that stretch beyond biological comprehension, Hydrogen peroxide and molecular oxygen accumulate in concentrations that would seem impossible under purely thermal conditions, while organic molecules of surprising sophistication emerge from reactions that proceed without benefit of catalytic surfaces or elevated temperatures. Only cosmic radiation could nurture such chemistry in conditions so hostile to conventional chemical processes. The gentle erosion of sputtering continues its atomic sculpture, removing individual molecules from the surface with such subtlety that the process remains invisible except when integrated across geological timescales. Each departing atom joins Saturn's tenuous E-ring, creating beauty from molecular destruction while gradually reshaping the very world from which it originated. The Moon diminishes imperceptibly, contributing its substance to the cosmic architecture that surrounds it through processes so patient they seem more like geological breathing than mechanical erosion. Between the quantum precision of individual chemical modifications and the astronomical scales on which their effects accumulate, Enceladus exists in states of being that transcend ordinary temporal experience. The radiation-induced changes that seem violent at molecular scales become gentle when viewed across the geological time periods required for their full expression. Cosmic rays write their signatures in chemical modifications that persist for periods longer than the existence of complex life, creating archives of environmental history that extend back to the solar system's earliest epochs. The ice sleeps in configurations that will endure longer than continents, preserving its molecular memories in crystalline arrangements that approach the theoretical limits of structural perfection. In the vast quiet between particle impacts, these frozen archives rest in mathematical stillness, waiting with the patience of astronomical time for whatever cosmic futures may eventually disturb their chemical equilibrium or recognize the information they have preserved across eons of invisible cosmic violence and gentle atomic transformation.